Welcome, everybody. This is the second edition of the Mosqlimate monthly seminar of six. Today we have Professor Dr. Flávio Coelho, our coordinator. Welcome. I will do a short presentation for our lecturer. So, Dr. Coelho holds a PhD in quantitative biology from the University of Texas at Arlington. He has served as an adjunct professor at UERJ, a visiting researcher at Fiocruz, and currently he's the principal investigator of the Mosqlimate team, an associate professor at the School of Applied Mathematics from the Fundação Getúlio Vargas, and data analysis coordinator of the Graph Network from the University of Geneva. So, welcome, Dr. Coelho. It's our pleasure to have you today with us, our coordinator. You have approximately 40 to 50 minutes. So, welcome. Thank you very much for your presence.
Thank you, Beatriz. Thank you, everyone, for having me and dedicating the time to watch my seminar today. This seminar is going to stay recorded, so yeah, I hope to reach even more people that couldn't be here today. So the title of this presentation is a bit ambitious. It should be called Power Laws and Prediction Gaps Towards a Statistical Framework for Extreme Dengue Outbreaks in Brazil, but I'm gonna try to bring some ideas and some preliminary results in this presentation about that will hopefully convince you that we need to be paying closer attention to this particular aspect of the statistical distribution of dengue cases, which, as I'm going to show, follow power law distribution. So for those who are not following this subject, dengue is a big health problem in Brazil, and we have an enormous amount of cases every year that we have to deal with, and it causes immense economic burden for the country. And our group and many other groups are focused on trying to help health authorities to prepare and to give early warning for measures from government that can help deal with this challenge in public health. So the problem with this is most of traditional statistical models that we use focus on one way or another. Of course, there's a huge variety of models. I cannot expect to speak for them all, but most of them will base their predictions on some average past behavior. And when you're talking about the distribution of past behaviors that are not symmetrical, which has a very long tail, such as a power law distribution, then the relying on averages and means and even medians sometimes is not enough. So if we want to have a brief idea of what I'm talking about, so this figure is from our last year's dengue challenge, and the colored lines are predictions from models that participated in that challenge, and in black dashed the line is the observed cases over those years, and you can see that 2024 was way above the average, or the I don't know, maybe the 90th percentile. Not sure, but it's quite big. So no model really managed to capture 2024, and that's a good example of what I'm just told you about. The problem with the type of distribution that these cases have. And so why power laws? So yeah, we could there are a family of heavy tail distributions that we could rely on, But power laws is a interesting one, especially because we can show that it for for the majority of the cases that we will analyze here today, it's the best fit, even when compared to log normals and other heavy tilt also distribution. So power law is a quite simple formula. It's defined as the probability normally as the complementary cumulative distribution function, which is the probability of a given variable. In our case, either the size of the epidemic of the number of cases per week is bigger than a given number, say X. And this probability, it tends to decay as X gets larger according to some sort of exponent, which we want to estimate when we fit power law distribution to our data. So the exponent alpha is called the scaling coefficient, and it is the only parameter. Well, not the only. There's another parameters associated with the fitting that I'm going to introduce in a little bit. But alpha is the main descriptor of what the distribution looks like, and it has been identified in other epidemics such as measles, pertussis, and mumps by Rhodes et al. Since a long time ago, and it has been also reported many other times since. But in Brazil, it's especially for dengue, it's very clear that we have such distributions, and if we look at annual case counts, the distribution of epidemic sizes, if you will, they tend to average across all cities at alpha equals to 2 point something, which is quite a healthy alpha for a power law distribution. And so when we talk about the power law, like as I said, there's another parameter of interest, which is what we call the X minimum, which is the minimum number of, see, if we're talking about the distribution of cases, for instance, which would be the minimum number of cases beyond which we have a good fit for the power law, because very small numbers tend to deviate for the power law, and also typically the very tip of the distribution, the observations, also doesn't quite match the theoretical maxima of the power law, which would go all the way to infinity. So yeah, so this is the top. We have a distribution for continuous power law, but there's also a version for discrete data. All of this is very well established in the literature, and that's what I used for the data that I'm going to show. So there's some literature about, as I said, I'm not going to detain myself in this because I want to get to the data. And the estimation methodology that we are using is based on the classical paper, now classical paper by Closet et al., which has been implemented multiple times, and it's available everywhere if anyone wants to fit power laws. It's the standard, golden standard for fitting power law to data. So I'm gonna now switch to data exploration format. See. Okay, so you can see here another screen of mine. So I have here a dashboard with some information about, I have actually all information from Brazil here. So here I'm showing you São Paulo, for those of you who are not familiar with the shape of São Paulo map. on this purplish map, we see the distribution of the alpha parameters. So we have alpha which are below 2, alphas which are higher, even close to 3. And here the median is for São Paulo would be 1.78. And that's over weekly cases over 15-year period. So I just pulled it all together. We'll have a chance to look at over time how this changes, but even when we just clump it all together, there's interesting patterns to see, especially in the spatial distribution. On the green map, you see how many epidemic years each of those municipalities have had over this 15-year period. And you see that there's some sort of a interesting one. This is low here. Here we have a high number of epidemics. And so there's some interesting correlations going on there that we should be aware of. If we look at the alpha values that are estimated and we plot it against the incidence, and this is annual incidence. No, this is average weekly incidence. It tends to grow. It tends to grow slightly, but significantly. But that's not true for all states. See, if I switch now, say, to Goiás, and we'll see a slightly different picture. But it is still interesting. First of all, we'll see that for Goiás, the median alpha is much higher, it's 2.22. And now the trend is gone. And if you look at how the alpha varied over this period of time, just in a very few spots it's growing, it's falling markedly, and the most of it, the map, it's either staying stable or growing very, very, very mildly. We can also look at clusters of alpha, which is quite interesting. And actually, the cluster map for São Paulo is even more interesting than this one. So this is one aspect of it, just to introduce you to the idea of how. So let me switch back to São Paulo, so just I can show you what I just said. Just to introduce you of what, how this power law way of distributed data, plays out across the Brazilian map. So if we look, let's look at so you see here that you have a cluster of high alpha values here in the west of São Paulo, as opposed to the southeast of São Paulo. This is quite well correlated with certain patterns of incidence, even though it might not look too clear when we just look at the figures right here. But yeah, it can explain some things. If we look at the level of the city, so let's think about São Paulo again. We could have there. I can look at I don't know, get a bunch of other cities here. Let's take I don't know. São José dos Campos, I don't know. I just picked this one for no particular reason. It has an alpha of about 1.9. It has had, since 2010, a very marked trend in increase. It's kind of hard to talk about an increase here because the data is quite scattered. So the R square is not very, very, very big. But anyhow, we see the fit. So this is the first time you see a fit of the power law. So here is the X minimum that I talked to you about. Normally, when we fit power law distribution, we disconsider the very low values here, because this is the part of the support of the data that is best for fitting the power law. And X-min is estimated alongside with alpha. So alpha and X-min are good indicators of how well or the particular power law that you have. And then you can also look at alpha versus some other aspects of the epidemics in São José dos Campos, for instance. We notice that alpha, as R naught gets bigger, alpha gets lower. That's pretty good. It's not too bad. This one has a very big point here. I forgot to put here the name of the city or that's the same city. Sorry. So that's 2024. So this is the outlier. So it's kind of hard to tell how it would go, because we're talking about here alpha versus total cases. So there's a big outlier that's 2024 that I already mentioned. So let's disregard that for now. But for other cities, that could be interesting to look. See, if you look at the association alpha with epidemic duration is also pretty good and ascending. For the beginning of the epidemic, also there's a trend there. And here is the sum of residuals here. It's not a traditional way of thinking of residuals. This particular residual here is the residual of the epidemic curve as compared when you match them, when you match it to a classic SIR curve. We do this for our Episcanner parameter database. So we calculate how well any real observed epidemic matches a theoretical SIR curve. So and we record the residuals. So what we're seeing here is that as we move towards bigger alphas, we have curves that depart from the traditional SIR shape. So that's an important aspect as well. So that's a quick look. We could be browsing cities here for a long time. We're not going to do that because we don't have time. But let's move then to some other way of looking at the scaling, because up to now we've been talking about fitting the power law to the weekly cases. So I take the distribution of the values, the number of cases observed each week, and fit the power law to that. So that's one particular type of distribution that does fit well to a power law. Another kind is this one. And again, I'm going to start with São Paulo here. And here is let me just adjust this. So, okay. We get a better, at least we can see the legend here. We can see here the fit is quite good. So each color here is 1 year. So we're looking now at the total number of cases. So the size, we're fitting the epidemic to the size of the epidemics every year on every city. So of São Paulo. So we have a color coding here for the year, and you can see that combined fit is 1.96 for São Paulo. It's a little less than for Brazil as a whole. And you see that for some other variables, and I put this just to show you that not everything is a power law. For instance, duration, it cannot be a power law because there's a limited duration of epidemic, so it can never have a big tail. So I just left this plot here so that you know what it would look like if the data was not power law distributed. So yeah, so here it's important, even though the alpha can be fit, when you look at the parameters, the goodness of fit for these parameters, which give, and here there's a p-value, and there's also a likelihood ratio value here against when you compare a fit of the power law against a simple exponential distribution. So we can evaluate goodness of fit. So even though we get a value for alpha here, we know that it's no good because there's no good fit. So moving on, we've tried to explore here some relationships with the alpha value with the size of the epidemic, which we already showed in a different way in the past part of this dashboard, but we can see here that seems to be some positive association, but that remains to be tested. Here, what I'm trying to do is to motivate everyone about the importance of this topic so that we can really dig in and test all these hypotheses more thoroughly. There are some things that are pretty hard for us to see because, like, again, if you look at all cities of São Paulo and the sum of that kind of residual we're talking about, yeah, it's kind of weird. Yeah, especially because of this city here, Ribeirão Corrente, which had a quite weird curve out there. Anyway, so I put this graph over here so that you know that even though these cities are quite well distributed according to a power law, that doesn't mean that they don't have a well behaved scaling according to their history a long time. So we have here the only year for São Paulo that we had more cases than the 90th percentile was in 2004. Before that, never crossed that line, that percentile. And then 2025 crossed it again a little bit more. So power law is not just, well, why I'm saying this, because just to say that power law is not just useful when you have huge out of scale epidemics. It helps us understand the smaller ones as well. So let's take a look at how can we use this in predictive modeling. So that's next step. So here I'm going to show you, actually I'm going to show two different models, this and the next one here. And those are going to be intentionally naive, simple models so that we can see, okay, if it works for such a model, then we didn't put much effort into tuning it. It can work much better for if I invest more time into it. So this model, I'm just trying to do point forecasts. So I'm trying to look at cases at time t base. In time t here, sorry, I'm not talking about from year to year. So I'm trying to predict next year based on this year. So T here is in years. So I'm gonna use this simple model to predict the size of the epidemic next year, the duration of the epidemic next year, and the week the epidemic peaked next year. And I'm using some lagged versions of this data, some the scaling factors, alpha and x min, from the power law fit. For the previous year, I could have used more years, but like I said, I was not worried about making this model as best as I could, but just to put something quick together, so to show you can see how good or bad this could be. So so there's some demographics, population, just basic population logged. They are not, and some climate. So when we fit this with just a random forest regression, and I already calculated this one, we could you see here, if we look at just the train data, it's quite good for predicting the size of the epidemic. Of course, when you look at the test sets, not that wonderful. For duration, it's slightly worse. It's slightly worse. For peak week, it's good. in sample, not so good out sample. So I painted reddish those points with largest errors bigger than observed minus predictive, bigger than an absolute values than 20% of the value. So deviation. So just so you know which cities are not a good match, because I wanted to look at the set of the misfit cities and see what they look like in terms, say, their population. They tend to be small, very small compared to the. Oh, hold on. See if I can zoom in here. Yeah. So if I can zoom in a little bit more, see they tend to be the vast majority of those misfits, they are below 100,000 inhabitants. So we could try to improve our fit and there's some residual analysis for the regression here. I'm not gonna go into that. And but so to mitigate this problem, I could try to exclude these points from the regression. I could, for instance, consider populations only bigger than 55,000. So then I can retrain the model and look at if it got any better. It will get a bit better, but not a lot. So why? Because mostly we need a better model with other predictors that can handle some of the structures that are still on the residuals that are not being handled by the model, the simple model that I put together. So yeah, so that's just to show you that uh, the power law metrics, they can be informative. So X-min is quite good, for instance, for total cases prediction. The alpha also, it's not so bad. The trend in alpha is absolutely not useful. But then again, the climate is it's nice, and there's some other epidemiological factors that help us there. So finally, let's move on to the second kind of a model that I want to talk about, which is a binary classifier uh, where I want to know, I want to be able to predict if next year is going to be bigger. Bigger than what? Bigger than a certain percentile, historical percentile. So I again using the same simple predictors that I had before, but now I'm building a classifier. So the output here is a bit different. So I'm first thing I have to tell you is that again I'm using São Paulo. I could have used other states, but just for us to be able to compare across models. So when you look at the confusion matrix, not bad. See, when you look at the classifier and look at confusion matrix, you want most of the mass on this diagonal here, because you want when it's a big epidemic, you say that it's a big epidemic. So here, yeah, I'm saying this most of the time. Not, I'm still being conservative. When it's going to be a big epidemic, I'm going to say no, it's not going to be. So yeah, so I'm still making a lot of mistakes here, and but hey, it's not bad. So if you look at the rock curve, which most of you certainly are familiar with, it's also area under the curve. Very nice. I mean, for this large data set with all this variability that we know it is, and the precision recall is also reasonable. The calibration curve tells us how overestimated or underestimated is our predicted probability of a big epidemic. So when we are in this region here below, say, the possibility beyond a fraction of, or a probability of 7%, uh, 70%, we get overestimation in here on our predicted probability. And on for higher, more likely case, we tend to underestimate the probability of having a big epidemic. And here because we want to be able to predict, we also apply some optimal threshold adjustment for the decision of the classifier. And then we can get results such as this one, where we get some cities that are really very likely to have a big epidemic on the following years. Let's zoom into a bit here. So here, sometimes I have to. So that's because I have this um, this the division between test and training and set in 2024. So I'm gonna get estimates for 2024 and the following year, 2025. So here, that's exactly what we have. So for this city, I have for 2024 a high probability red of 0.5, which is way above, not way above, but above the our classification threshold. And I forgot where I was. And for 2025, it's not considered. It's on the blue, so it's not considered um, big epidemic. Um, so if I move. Yeah, if you want to play with this, if I move down here, I can get more predictions for the years after. I'll train a model for the previous years and then train from then on. So 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 these are the explorations that I've done so far, and that lead me to the idea that we need to find ways of handling this, because if we don't handle it, we'll end up continue to have to explain why we can't actually predict the years that are too high in incidence. So let's move on then to some try to summarize some of the results. Some of these results are not really settled in, set in stone yet, because I really have to explore a bit deeper. But these are, you could take them as hints that I think are leading to interesting facts. So we have significant spatial variation, so that's good, and that can explain some of the variation and the burden of dengue across space. And we've noticed that states with low alpha have more extreme outbreaks, more frequently extreme outbreaks, as we saw the distribution of R naught versus alpha, remember that? So, and higher unpredictability potentially. So that's why I put the question mark here. We need to look into that more carefully. And contrarily, I mean, complementary, if we have high alpha, we might have more predictable epidemic dynamics with fewer extreme events. It needs to be looked at more carefully. One of the challenges that we have here, as you've seen, there's a huge amount, it's a boatload of data. That's why I put this presentation in the form of a dashboard so that we could really browse. Unfortunately, we don't have enough time to browse through many cities or many states, but the idea is that we have to find ways of navigating this mountain of data so that we can find generalizable conclusions that we can stand by. In terms of the interpretation of alpha, I've already mentioned this, and this is in line with Rhodes' classical paper that also had this finding. He used the parameter tau in his paper, and yeah, and for dengue, we find that beside the geographical variation, there's also associations with climate, demographics, and immunity, of course. So as a key insight, we could say that a map of alpha might serve as a risk atlas, something that can point you to regions that need further attention that we need to be careful about going forward. And especially when we looked at those spatial cluster maps, that really it can be really informative. In terms of temporal evolution of alpha, we've seen the longitudinal scales and if we look across many cities, which I couldn't show you many cities today, but I've looked through many cities, we can see that there are there are some patterns in the trends, and some of those trends are associated with some other characteristics of the cities. So that's something that we need to explore more. And the interesting thing about this is that I'm looking at these things across 15 years. So these patterns they represent when we correlate them with these other parameters, they correspond to consistent patterns across more than a decade, and that's very important to remember. So they're consistent. So we could run some sort of a trend analysis and try to associate this with some predictive thing. This is just an idea. As we look at the epidemiological correlations, I've shown you an example. R naught is linked to tail thickness, or the alpha, the value of alpha. So higher transmission intensity is associated with heavier tails, which mean like more aggregated distribution. For total cases, alpha is inversely related to attack rates, which is the total number of cases in a given locality over the year. And so cities with lower alpha will experience larger cumulative outbreaks. All of this is not really easy to explain, but it's a starting point for us to think about why this should be so. So that's a question that I'll leave to you because I still don't have an answer to them. So for epidemic duration, we also have correlations. Again, onset timing. I showed you all those plots. And again here, the model residuals, like I said, when you compare the epidemics with a theoretical SIR curve, power law dynamics, power law scaling, the power law, the degree to which the distribution approaches the power law, and the parameter of this power law will define a certain degree of departure from the theoretical curve. And why is that? Let's find out. I don't know. So this is what I decided to call the prediction gap. We have a prediction gap if we don't look at this aspect, this distributional characteristic, and that's what I think we should move towards. Let's fill this prediction gap. So this, I think, it's one of the important factors that will help us fill this gap. So yeah, one other aspect that when we think about the power law distribution, I think some of you might have already realized this. we're not looking at one aspect of the epidemics. We looked at distribution, at least two, weekly case counts, which is a very good fit for power law, but also the total epidemic size also very good fit to a power law distribution. Epidemic duration, on the other hand, exhibits some scaling behavior, but with different, with different type of long tail or asymmetric distribution, which might be easier to handle if you want to predict epidemic duration. So, there's a number of other things that we can still do based on looking at the combined complementary cumulative distribution function. For instance, when we look at this distribution, and if it fits so well, especially in when you above x min, it gives you a little bit of confidence when you make predictions for how likely are bigger epidemics to happen, like I showed in the last model. So yeah, we could try this in different ways, and perhaps looking at more disaggregated or aggregated fits to the data and leading to different results. So in terms of what we've done so far in terms of predictive modeling, we've shown that even if we're a very naive model, we can actually get reasonable predictions from one year to the other. We explored not only Swiss Army knife random forest regression, but also tried some quantile regression, which were not that better, but they might work better for if you're trying to predict higher percentiles than the median. But still, we've tried this, and there might be other targets that could be helped by the knowledge of this distributional parameters. I've explored the size, the duration, and the peak week, but there might be others. So one other thing is that once we look at this data that is fit across aggregated data from the state, we see that there's good agreement of this distribution curve across orders of magnitude. So that tells us that perhaps the models that are fit and on aggregate data in this have more data to achieve a better fit might be used for predictions on cities of different sizes. So we're no longer locked into having tailor fit models to certain size categories of targets. So that's something to think about. Yeah, I have some other things here listed, but I don't think they are really that important. I perhaps talk a little bit more about this idea of the subset of the cities which are called in the dashboard, and we were looking at the dashboard as misfits, the one that we didn't quite predict well. And I looked at them from the lens of, are they big or are they small? Because we had already bumped into this issue that very small cities are particularly challenging for us to predict, especially not only because they have more noise as in proportion to the amount of cases that they have, but also because they usually don't have long histories of epidemics that let us know exactly how they behave. So we still have a challenge of how to deal with this extremely this lower limit of population sizes. It's something that remains a challenge. The power law it tends to cover better the above a certain minimum size. Um, so yeah, so this the a little bit more details about the size classification model that we did. So we looked at we tried to predict if the size was bigger than a certain percentile of the historical data which we use for training the model. The figures I showed you, I used this threshold as a 7/5 percentile, which is quite ambitious because, as we've seen from for São José dos Campos, I think I showed you, it's very rarely that they go above 75% of the historic distribution. So perhaps a more reasonable model would look at above 50%, above median, or above a slightly, maybe 60%. I don't know. So something that it remains to be seen. Well, what makes more sense in terms of on the other hand, if you're just predicting above a median, perhaps it's not cannot be called extreme events. And sometimes extreme events have a value of their own because they can be a really a real problem for governments and in terms of their economic burden and health burden. But so those are here. I'm gonna go let you read this. Those are the details of the way that we implemented those models. And yeah, so again, there's no particular uh, care put into trying to fine-tune these models, just to see how a off-the-shelf model would use that information. So in summary, finally, I think I've summarized 2 or 3 times already. So power law is clearly pervasive and across the whole country. You cannot say it's not a very common phenomenon, even though the estimated alpha can vary quite a bit. Uh, the the literature on power distributions consider them all as power law distributions, but with different parameters. But if you go too low on alpha, then there's an argument that that kind of distribution could be better fit by a log normal or by an exponential, a less extreme long tail distribution. So spatial heterogeneity shows very interesting patterns that can be used. So we need to understand this, and especially if they are linked to the risk of extreme outbreaks. The temporal trends clearly show that somehow these cities are either moving consistently up the alpha ladder or down for some reason, which is not clear to this at this time. And it's something, a very interesting point to explore as well. So we need to explore these prediction gaps, not only for cities with heavy tails, but for all values of alpha, really, and see how they can improve predictability. So there's room here to run a more detailed analysis where you look the importance of alpha as a predictor as we move through uh, through different types of distributions. And I think we've been able to show that using these parallel features can improve forecasting, and they are pretty good at classifying, at predicting big epidemics. So with that, I would think that the implications of all this is that, again, we need to look at these distributions. We have to try to figure out if using alpha for resource allocation makes sense. And also we have the challenge of explore different models that can use this information and then try to elaborate on size classification models to be able to help with early warning systems. Perhaps that would help us close a bit of the gap of not being able to say anything about huge epidemics. If we can have a probability of having bigger than 75%, bigger than 80%, I think that's an important thing. If we can show that these models can detect 80% of the cases, that's awesome. That's much better than most models out there. So finally, I'd like to acknowledge our research group, which is mostly here in this meeting, the Brazilian Ministry of Health, and for their support to InfoDengue, and to InfoDengue itself for the surveillance data that we use, the Fundação Getúlio Vargas for support to myself and my students, and the Wellcome Trust for funding the Mosqlimate project. And to end this, I will leave you with this call for our third InfoDengue Mosqlimate Dengue Challenge, which is already open for registrations up until May 15th. So you can register a team to create your own model to predict the 2027 dengue season in Brazil. Thanks a lot, and I hope to answer some questions now.
Thank you very much, Flávio.